This video is the part 2 to our class meeting for May 4th. It was a good break point in the video because this really is, I think, the last wave of knowledge that we want to put forth, is digging a little deeper into the nature of water and understanding a little bit more, perhaps even mathematically, what pH is. So here we go. The essential idea. Now, I don't know where I lost the original essential idea. Oh, there we go. Okay, so let's start over here. Pure water self-ionizes. We have definitely done that a couple different ways in the practice sets and in the previous class meeting videos. And so you have in pure water a very small number of species of components that aren't H2O. And what these are is they are the hydronium ion, H3O+, and the hydroxide ion, OH-. And in fact, this little clip right here comes from that PhET simulation. So think of the beaker of water, think of that big magnifying glass I have in front of it, and I just went right in to a spot that showed a representative hydronium ion and a representative hydroxide ion. Those are present in pure water in very small quantities. So that I think we had talked about. In terms of starting to look at the math of it a little bit, the very small quantity in which both of those are present is 10 to the minus 7. Now, what I'm ignoring there is I'm ignoring the units of concentration. So just as an aside, that would be 10 to the negative 7 moles per liter of water. Moles we explored a little bit earlier in the year. We really needed to get back to that, and I hope we are able to do that. But I'm just going to call them concentration units because I'm focused on the 10 to the negative 7. And I think we can agree that 10 to the negative 7 is a very small number. In fact, I think you'll have questions on your assessment that say, oh, convert 10 to the negative 7 to a number presented as a decimal. And I can often be off by 1 0 when I initially do it. So I think I'm going to do 6 zeros here and then the 7 and that, then the 1. See if that's a winner. So this number right here is 1, 2, 3, 4, 5, 6, 7. Okay, so this is the decimal form of 10 to the negative 7. So that's a small number. So when I mentioned that in pure water, which is what this is, there's a very small number of hydronium ions and hydroxide ions. It visually looks like a very small number because you can see all the water molecules in the rest of the water as done by this person who did the simulation. All these light gray things are the water molecules. And you have some very small number of hydronium ions and hydroxide ions. And so that very small number happens to be 10 to the negative 7. And when you write it like that, the fact that that exponent is negative 7 is why the pH is assigned 7. Okay, that's worthy of a lot more, but let's see if I can go through an example or two. Okay, so the pure water has the 10 to the minus 7 concentration units of hydronium ions, and it has 10 to the negative 7 concentration units of hydroxide ions. Now, why are they the same? It's the same because it's pure water. And so for every 2 water molecules, that very small number that happen to self-ionize to make these ions, you're going to produce one of each. So when you think about it, it's no great surprise that the concentration of the hydronium ion and the concentration of the hydroxide ion in pure water, they're both this very small number of 10 to the negative 7. Okay, and pH specifically is referring to the hydronium ion concentration. Because what we see in this last essential idea is that in aqueous solutions, so now you've got solutions where water is the solvent and you're putting something in it. And if you put in an acid or an alkali, it disturbs the balance between the hydrogen ions, or H3O+. Right, those are often used synonymously. It throws off the balance between the hydronium ions and the hydroxide ions. And it's going to change the relative amounts. And that's what the pH scale is used to represent. So let's suppose, so we've got these 2 last questions that take us through a little bit of the math of pH. And I think if you understand it mathematically, that can help in your overall chemistry understanding of pH. So we have an acid solution, and it says the concentration of hydronium ions is 10 to the -4. So can we write that as a decimal? And that's 0.0001. That is 10 to the -4. So let's see, tens, hundreds, thousands, 10,000. So that's 1/10,000th. So it's going to be 0.004 concentration units of hydronium ions. That is greater than 0.00000001, or 10 to the -7th. So I have more hydronium ions than I usually would. And so that's characteristic of an acid. Because if an acid is dumping, so to speak, these H+ ions in your what was neutral water, you're going to have a whole bunch more hydronium ions because those H+ is immediately attached to waters. Okay, so what's the pH of this solution? Well, when the concentration units, the number is 10 to the -4, that's going to give me a pH of 4. It's the opposite of the exponent to the extent that we're looking at it here. We're looking at concentrations. I'm always going to give you 10 to the -3, 10 to the -4, 10 to the -5, 10 to the -7 for neutral water. And so the pH of this solution is 4. And again, that fits our model, right? Because we know that if the pH is less than 7, then it's acidic. So what we've done there is we've started with pure water, pH 7. pH 7 means the concentration of hydronium ions is 10 to the -7. pH of 7 means 10 to the -7 is the concentration of hydronium ions. So as a decimal, that's 0.00000001. But then we add acid to it. That increases the number of hydronium ions. And so this number here is a larger number than 10 to the -7. 10 to the -4 is a larger number than 10 to the -7. And so what we've got is we've got a higher concentration of hydronium ions. And that creates, by how we're looking to interpret a concentration and create a pH from it, you can see that this bigger number, 0.0001, re-expressed as 10 to the -4, that is a pH of 4. That represents a pH of 4. So our pH has dropped. So this is the math behind how the hydronium ion concentration can increase, and yet the pH drops. Okay, so then I'd also like students to appreciate that it is a balance between hydronium ions and hydroxide ions. So in neutral water, you have equal numbers, but there's a balance between them, and if you increase one, you decrease the other. So what happens here is, in this same solution, tell me about the hydroxide ion concentration. Well, if the hydrogen ion or hydronium ion concentration increases, that means the hydroxide ion concentration decreases. So this is decreases. It looks like this. I forgot to do the superscript, so that's supposed to be 10 to the -7. So in the problems I can imagine giving you, they would be outlined something like this. I'd tell you about a certain aqueous solution, meaning water's the solvent, and we're going to disrupt the balance between the hydronium ions and hydroxide ions. And if you do something that increases one, it necessarily decreases the other. That's the maintaining the balance. So, and then we can give you the questions where you actually have a mathematical concentration value and you can figure out the pH. And fascinatingly, when we increase the concentration of hydronium ions, we're going to see that that actually drops the pH. But we need some practice problems to play with for that, so that will be part of the practice set for today. And I think that's getting near the content that we would want to present for the unit. So thank you.